This is Lab 2, Motion of a Falling Object. The main purpose of this lab was to determine the influence of the drag force on a falling object and compare it to a model that did not account for drag force. Every object on Earth is under the effect of gravity, which is a force of magnitude mass times gravity in the negative y direction. Drag points the opposite direction of gravity in the positive y direction and has a magnitude that is proportional to the square of the object's speed. Drag occurs because of the air resistance on an object's surface as it is falling. As will be seen later, the force of drag is ultimately unavoidable for certain objects and must be accounted for in real-life experiments. The fundamental physics principles that can be seen in this experiment include Newton's second law, which states that when a net force is zero, a body does not accelerate according to F equals ma. The gravitational force is used to show acceleration, and the initial velocity is zero and speeds up, suggesting that a non-zero net force exists and the body is thus accelerating. The drag force is evident as there is acceleration, and the net force is therefore not zero. And generally, a larger surface area indicates a larger drag force. Here, there's a paper ball that is falling, initially starting from rest. The paper ball is considered to be the system, while everything else is considered to be the surroundings. Here's the initial data for both of these simulated models. The start time is directly pulled from the data table and tracker. The initial position was made into a vector, only accounting for the y position. The initial velocity was 0, 0, 0 since the object started from rest. Each time interval was approximately 0.0167 seconds, as mentioned earlier, until a final time of 0.683 seconds was reached. Here we can see that the observed and simulated plots are similar. The red is simulated and the blue is observed. It appears that they start at similar positions, but the observed position is higher at the end compared to the simulated no-drag position. This discrepancy suggests the influence of another force. This could be due to the effects of air resistance or due to any random gusts of wind. When the coding was done without drag, the ball position started at a height of 0.033 meters. The time started at 0 seconds and was increased at an interval of 0.0167 seconds. The b value, or the proportionality constant, was set to be 0, as in this case we were not accounting for drag or air resistance. The while loop starts at t equals 0 and goes until 0.683 seconds have passed. In the loop, the net force is first calculated and then the velocity is updated using the velocity update formula, followed by updating the position in the position update formula. Lastly, the time is advanced by adding the change in time to the current time. This is all done while b is still equal to 0. As mentioned earlier, the system in this experiment is the paper ball and everything else is considered the surroundings. The ball initially begins at the point 0.031 meters and is falling from rest. The ball is accelerating, suggesting that some other force is acting on it, and this force is likely the drag force. Here's a graph with the observed, simulated drag, and simulated no drag. As can be seen, the yellow and blue dots seem to be more in line, suggesting that the drag model was a more accurate representation of the experiment. There is still a slight discrepancy which could have been due to the camera angle off-putting the axis or other environmental factors. The coding for the drag remains mainly the same, except the proportionality constant is changed to the square of the ball's speed, which accounts for the drag. Here, everything remains the same except for b, which again is updated to the magnitude of the velocity squared or speed squared. In conclusion, what does it mean? The model with drag demonstrates a terminal velocity considering that the force of drag matches the force of gravity so that the net force on the object is 0. The model without drag will accelerate due to gravity without an end. What if? The top graph is the velocity time graph for being dropped from rest, whereas the bottom is thrown downwards with an initial velocity of -1 meters per second. As seen, the terminal velocity remains the same in both scenarios, coming to around -3.1 meters per second, suggesting that this does not affect the terminal velocity.